Now, let's look at fairness and truthfulness in pricing. Fairness and truthfulness are important for data product markets. Recall that fairness refers to that the revenue generated by a sales transaction in the data market is distributed to sellers in an unprejudiced manner so that they are paid for their marginal contributions. Truthfulness means a market where buyers are well motivated to report their internal valuation of the data products unrarely. Agora proposed a mathematical model of data markets that are fair, truthful, revenue maximizing, and scalable. They assume each seller J supplies a data stream Xj. Each buyer N conducts a prediction task Yn. Xj and Yn are vectors of length t. For example, Xj may be a stream of customers' interest on different products, and Yn may be a task of predicting a new customer's interest. Taking a prediction task Yn and an estimate Yn hat, a prediction gain function Gn is from r to the power 2t to the range of 0 and 1. This function measures the quality of the prediction, the value that the buyer is willing to pay for a unit increase in G. A machine learning model M from r to the power of mt to r to the power t uses data from M sellers to produce an estimate Yn for buyer N's prediction task Yn. Let Pn and Bn be the price and the bid respectively. Then, a location function AF from Pn, Bn, Xm to Xm tilde measures the quality at which buyer N obtains that is allocated to the sellers on sales Xm, where this Xm tilde is in the domain of r to the power m. Revenue function RF, defined as shown in the slide, calculates how much revenue Rn to extract from the buyer. The utility buyer N receives by bidding Nn for Yn can be calculated by the formula here. A market is truthful if for all prediction tasks Yn, this mu_n is the argument maximizing this u_z_yn. In this study, the authors adopt the notion of fairness following the famous Shapley fairness. One main result is that the data market defined as such is truthful if and only if function AF star is monotonic. That is, an increase in the difference between price rate Pn and the bid Bn leads to a decrease in prediction gain G. They also give randomized epsilon approximation algorithms for fair data market. That is, the difference between the Shapley value and the estimation is less than epsilon with probability 1 minus delta. Their algorithms are polynomial. Shapley fairness is popularly adopted as the foundation of fairness in data markets. However, computing Shapley's Shapley value is exponential. Maliki et al. Presents a permutation sampling method that approximates Shapley value for any bounded utility functions. The basic idea is to use the previous equation, permutation-based equation of the Shapley value, and tackles the problem of this theta s as the expectation of u p s pi union s minus the u p I pi, as shown in this figure. And then we can do the sample and use the sample mean. Following Hofstad's inequality, to achieve an epsilon delta approximation, we only need 2r squared n over epsilon squared log 2n over delta samples and evaluate the utility function on squared log n times, where r is the range of the utility function. Jia et al. Present approximation algorithms for Shapley value that can substantially reduce the number of times the utility function evaluation. First, they apply the idea of feature selection using group testing. For user S, let beta S be the random variable that S appears in a random sample of sellers. Then, for sellers Si and Sj, the difference in Shapley values between Si and Sj is given by the formula on the slide. They can use group testing to first estimate the Shapley differences and then derive the Shapley value from the differences by solving a feasibility problem. They show that this algorithm is an epsilon delta approximation evaluating the utility function at most O square root n log n squared times. They further observed that most of the Shapley values are around the mean. Exploiting this approximate sparsity, they give an epsilon delta approximation algorithm evaluating the utility function only on log n log n times. Gopany and Zhou propose a principled framework for fair data evaluation in supervised learning, and Monte Carlo and gradient-based approximation methods. Their Monte Carlo method follows a general idea similar to that in Jia et al. They generate Monte Carlo estimates until the average empirical coverages. They also argue that, in practice, it is sufficient to estimate the Shapley value up to the intrinsic noise in the predictive performance on the test dataset. Adding one tuple as a training data point does not significantly change the performance of a model trained using a large training dataset. Therefore, truncation can be used in practice based on the bootstrap variation on the test set. In their gradient Shapley method, they train a model using one epoch of the training data, and then update the model by gradient descent on one data point at a time, when the marginal contribution is the change in the performance of the model. In general, computing Shapley value requires an exponential number of model evaluations. However, for some specific models, the computation may be reduced dramatically. For example, Jia et al. Show that for unweighted KNN classifiers, the exact computation needs only on log n times. Time and epsilon delta approximation can achieve in on to the power of h epsilon k log n time when epsilon is not too small and k is not too big. They also propose a Monte Carlo approximation of O n log n squared over log k squared for weighted KNN classifiers. A key enabler of the progress is the specific utility function of a KNN classifier. We can rewrite this utility function in the formula shown on the slide. Here, alpha is the index of the chaining feature that is the kth closest to X test among the chaining examples in S. Moreover, the sublinear approximation for unweighted KNN classifiers is facilitated by locality-sensitive hashing. Related to fairness and truthfulness in the market, cooperation among different agents in the market may happen. Building trust in a sub-community within a data marketplace becomes an interesting subject. Armstrong and Durfee analyze factors that may influence the efficiency of building trust and conducting cooperation in the data market. For each agent in the market, the other agents can be divided into two categories, naming those remembered agents and those strange or forgotten agents. They have a few interesting findings. Cooperations arising from iterated interactions is inversely proportional to the rate of system missing. The number of initially misbehaving agents and the rate at which agents explore alternative strategies. Cooperation is also initially inversely proportional to population size. At the same time, cooperation is proportional to average member size, and better estimation of the likelihood of strange agents to misbehave. Now, let's turn to another big topic, privacy preserving marketplaces of data. Privacy is a serious concern and also a critical tipping point in designing marketplaces of data. First of all, when a data user shares her or his data with some others, more often than not, the user may disclose her or his privacy to some extent. Therefore, it is important to explore how to protect or minimize the privacy leakage. At the same time, it is also important to understand how a seller's privacy disclosure may be properly compensated through data pricing. Ghosh and Ruth designed truthful marketplaces where data buyers want to purchase data to estimate statistics and sellers want compensation of their privacy loss. In the design, there is only one query and the individual evaluation of data are private. Data owners are asked to report the costs for the use of their data. Under the assumption of differential privacy, they transform the problem into variants of multi-unit procurement auction. They show that when a buyer holds an accuracy goal, the classic Vickery auction can minimize the buyer's total cost and guarantee the accuracy. When the buyer has a budget, they give an approximation algorithm to maximize the accuracy under the budget constraint. The method by Ghosh and Ruth may not work well when the cost and the data are correlated. For example, a store with more customer traffic may request a higher cost in using the data. Then, reporting the cost may reveal the privacy of the store. Fletcher and Loy tackled the scenario where costs are correlated with data. They propose a posted price-like mechanism. Given a set of data sellers categorized into different types and the associated distribution of costs, the mechanism offers each user a contract with the expected payment corresponding to the type. If a seller takes the offer, the payment is determined by seller's verifiable type and the associated payment in the contract. All sellers have the same probability to take or reject their contracts independently. The sellers are truthful, that is, a user will take the offer if the payment is larger or equal to the privacy lost. This posted price-like mechanism is Bayesian incentive compatible. That is, every seller's strategy is Bayesian Nash equilibrium. It is also interim individually rational, meaning the expected utility is non-negative for every seller when the seller decides truthfully. It is O epsilon to the power minus 1 accurate, perfectly data private, and epsilon differentially private. Here, when we say it is perfectly data private, we mean whenever the mechanism's posterior belief about a seller's data differs from its prior belief, the mechanism pays the seller. Lee et al. Tackles the same problem as Ghosh and Ruth do. But they assume that individual valuations are public and focus on returning unbiased estimations and pricing multiple queries consistently. To address the concerns on privacy loss, they develop a theoretical framework to divide the price among data owners who contribute to the aggregate computation and thus have loss of privacy. Their framework extends several principles from both differential privacy and query pricing in data markets. Liu et al. Further consider the scenario when multiple sellers' data are correlated. They extended the fairness defined by Lee et al. To dependent fairness. The fairness mechanism in Lee et al. Only compensates a seller whose data are used. In dependent fairness, a seller S is still compensated if the data of another seller S pi are used that are correlated with the data of S. They propose two approaches to privacy compensation. In the bottom-up approach, the broker first satisfies each individual seller's privacy compensation and then decides the price for the statistic selling to a buyer. In the top-down design, the broker decides the total price of a data aggregate product sold to a buyer and then spares a fraction of the total price for privacy compensation. The privacy compensation is divided and assigned to individual data sellers by solving a budget allocation problem. Each seller receives a compensation roughly proportional to the privacy loss due to the data sharing. Liu et al. Further extend to time series data that may have temporal correlations. They adopt pufferfish privacy to measure privacy losses under temporal correlation. While various efforts have been made to address the challenge of privacy loss compensation when user data are correlated in one way or another. As Ghosh and Ruth point out, in general, it is impossible for any mechanism to compensate individuals for privacy loss properly if correlations between their private data and their cost functions are unknown beforehand. In the classical setting of physical goods, contract theory with hidden information, that is, unobservable types of buyers, the seller designs a set of contracts with different consumption levels to maximize revenue from buyers. Lajchet and Sinha extend the contract design model to price a bundle of queries at different privacy levels to maximize revenue. At the same time, they also consider adversarial users. Their work also adopts differential privacy. For query bundle Q1 to Qk, a contract is a tuple P, epsilon, and S, where P larger than 0 is the price paid by a buyer, epsilon is the privacy budget, such that a buyer can get answer to query Qi with epsilon I differential privacy guarantee, and epsilon is larger than or equal to the sum of epsilon I over all k queries. And P is the post-hoc fine to be paid if a buyer is found misusing the query answers. It is assumed that an adversarial buyer derives a benefit C epsilon, which is monotonically increasing and convex. C0 equals 0. One interesting finding is that in the traditional contract theory, if there are n types of honest buyers and one type of adversarial buyers, the seller should design up to n plus 1 contracts. In the data marketplace situation, they show that up to n contracts are sufficient. In other words, a data seller should not design a contract for the adversary. Instead, the seller should adjust the contract's pricing to account for the risks for adversarial users. They also design post-hoc fines in pricing query bundles that can help to reduce loss due to privacy leakage by adversarial buyers. They provide a fast approximation algorithm to compute contracts. A data owner has to decide a trade-off between privacy and data utility. Lee and Raghunathan designed an economic based incentive-compatible mechanism for a data owner to price and disseminate private data. Specifically, let two-part tariff pricing function RSX equals to alpha S, which is the fixed part, and beta S times X be the flexible part, be this price function for X amount of data with sensitivity level S, where this alpha S and beta S are the fixed and variable price factors respectively. Assuming two types of data users, one type for aggregate queries and patterns in data, and the other type for individual identity and personal information, the proposed mechanism works in 4 stages. First, the data owner selects a variety of sensitivity types to offer. Second, the data owner offers different prices for data with different sensitivity types. Third, a data user selects a certain sensitivity type with corresponding price, and thus reveal the user type. Last, the data user selects the optimal amount of data with the chosen sensitivity type. The core idea here is that the data owner can identify the sensitivity attributes in the data, such as the identifying attributes, which are not useful for aggregate analysis, but necessary at individual communication. A data owner can offer a low price for data without those sensitive attributes and charge for a higher price for data with sensitive attributes. This approach provides an orthogonal idea to the popular ways of tuning the parameter in differential privacy. Due to the privacy concern, when a company may have opportunities to collect data about its customers, should it do it? That means collecting and reviewing data, or not do it, meaning a blanket policy of never collecting. Ginsing et al. Find that the company should not collect customer data if the total gains from trading the data cannot cover the privacy loss. In practice, there is an increasing tendency for customers to overestimate their loss of privacy, particularly when the use of the private data is uncertain. In other cases, the company should offer two contracts on their services and products. One of the contracts collects the customer data at a certain price, and the other contract does not collect any customer data at a different price. While most of the studies on privacy-preserving data marketplaces focus on the privacy of data owners, transactions may also disclose privacy of data buyers, such as what, when, and how much they buy. For example, a retail company purchasing query results may be considered what queries like the product items or customer groups involved in the queries, when, the periods where the queries are concerned, and how much data it purchases as privacy, and may want to keep the information confidential from any others, including the data sellers and brokers. ILO et al. Designed a mechanism such that after making an initial deposit and maintaining a sufficient balance, a buyer can engage in an unlimited number of priced oblivious transfer protocols where the seller and the sellers and broker cannot know anything other than the amount of interaction and the initial deposit amount. The broker even cannot know the buyer's current balance and when the buyer's balance runs out. This is achieved by adapting conditional disclosure to the two-party setting. Distribution and use of private data are another important step where privacy may leak. Hennis et al. Demonstrates Sterling, a decentralized marketplace for private data, which supports privacy-preserving distribution and use of data. The central technical idea here comes from privacy-preserving smart contracts on a permissionless blockchain to provide strong security and privacy guarantees. They combine the blockchain smart contracts, trusted excursion environments, and differential privacy. Particularly, smart contracts allow enforcement of constraints on data usage and enable payments and rewards. Now, let's look at pricing dynamic data and online pricing. Many applications are built on dynamic data and online data. How to price views on data streams properly is an important issue for practical data markets. One central task is to estimate and optimize the operational costs, which are the costs to evaluate queries of different users on the fly. The pricing decision involves not only data sellers but also data buyers. For example, suppose two data buyers B1 and B2 purchase two queries Q1 and Q2, such that Q2 can be written as a further selection on top of Q1. For example, Q1 is about all customers in North America, while Q2 keeps all the same as Q1 but focuses on only customers in Canada. The optimal pricing of Q1 and Q2 should take the advantage of the overlap between the two queries so that the sharing can save the operational cost, and at the same time be fair to both B1 and B2. L. Kingswani et al. Proposed a greedy method that enumerates all possible sharing plans and selects the one with the minimum additional cost. It does not come with any quality guarantee. Liu and Hakikumas propose an improved method that takes some risk in sharing plan. If the costs of the previous sharings are already accumulated to a high level, and the additional cost of a new sharing, that is the risk, is moderate and can be amortized well by the previous sharing, then the new sharing may be taken. They also give 5 rules to ensure fair pricing. Let ACS be the cost attributed to a sharing S. First, for two identical sharings S1 equals S2, ACS1 should be equal to ACS2. Second, for any sharing S, ACS should be no higher than the lowest cost of S if no other sharing exists. Third, for two sharings S1 and S2, if the query of S1 is contained by the query of S2, in other words, the result of S1 is a subset of the results of S2, and the lowest cost of S1 is smaller than the lowest cost of S2 if no other sharing exists, then ACS1 should be no more than ACS2. Fourth, a sharing plan with common sub-expressions with other sharings should be compensated. Last, the cost of the global plan should be equal to the sum of costs attributed to all sharings. In order to purchase dynamic data, a buyer may have to call a seller's API repeatedly. A buyer may have to pay for the data multiple times. Unpadhyaya et al. Explored how to modify APIs to achieve optimal history-aware pricing. That is, buyers are charged only once for data purchased and not updated. The central idea is that the introduction of the notion of refund. A user can ask for refunds of data she or he has brought before. For each query, the seller issues a coupon in addition to the query result, where the coupon records the identity information of the data in the query result. More specifically, coupon C equals ID, UID V, and tau and H, where ID is the tuple identifier, UID is the user ID, V is the version ID that is monotonically increasing, tau is a query identifier that is monotonically increasing too, and H is a cryptographical hash function, such as SH1, SHA, Q256, and SHA3. And kappa is a secret key only known to the seller. If a buyer gets two coupons, C1 and C2, in two different purchases, such that C1 and C2 match in TID, UID, and V, then the buyer can ask the seller for a refund by showing the two coupons. As they point out, the refund mechanism does not provide any arbitrage-free guarantee. In Quran, they can support history-aware pricing. To incorporate a query history, suppose a buyer already purchases queries Q1 equals Q1, Q2 to Qk and pays for a total of PQD so far. When a new query Qk plus 1 comes, let the support set Sk plus 1 equals to the formula in the slide. Then the new total price P can be updated accordingly. This history-aware pricing function is shown arbitrage-free. Zhang et al. Consider online pricing for mobile cloud sensing data markets. Different from most of the work on data markets, they assume that data providers distributed in space and three types of spatial queries from buyers, namely single data query, multi-data query, and range query. Single data query is a query that the value at a specific location. Range query is the probability that the data at a region falls in a given range. Multi-data query is the mean in a region, and range query is the probability that the data at a region falls in a given range. The vendor uses the raw data from data providers and produces a statistical model through Gaussian process to answer queries. To form different versions of data products, the vendor generates different conditional Gaussian distribution with respect to locations and uses the conditional entropy to quantify the quality of the versions. They propose a randomized online pricing strategy so that the price can be adaptive from the historical queries. They show that the pricing mechanism is arbitrage-free and is a constant factor approximation of revenue maximization. New et al. Consider online data market where a query may be sold to different buyers at different time, and the broker can adjust prices over time. The objective is to maximize the broker's cumulative revenue by posting reasonable prices for sequential queries. They design a contextual dynamic pricing mechanism with the revenue pricing constraint. The central idea is to use the properties of leads sold for efficient online optimization. Their method can support both linear and nonlinear market value models with uncertainty. In summary, in this section, we review the topic of pricing data products. We first analyze the structure, players, and ways to produce data products in data markets. Then, we examine several important areas in pricing data products, including arbitrage-free pricing, revenue maximization pricing, and fair and truthful pricing. We also discuss how to price dynamic and online pricing. When pricing data products in a marketplace, those several considerations are typically incorporated and integrated in one way or another. Thank you.